In today's video, we'll be discussing heat. When you touch a hot stove or drop ice into a drink, energy is moving. That energy is called heat. In this video, we'll break down how heat is transferred, how to calculate it, and how phase changes are involved. By the end of this lesson, you'll be able to calculate exactly how much heat is involved. So what is heat? Heat is the transfer of thermal energy between systems or objects due to the temperature difference. It always flows spontaneously from the hotter to the colder areas. You can also think of heat as the total kinetic energy. If there's no kinetic energy, there's no heat. Heat is going to be measured in joules or calories. One small calorie is equal to 4.184 joules. A small calorie is not a dietary calorie. A dietary calorie is 1,000 of these small calories. Temperature, on the other hand, is the average kinetic energy. We will let the letter Q represent heat. I have two basic formulas. Q equals mc delta T and Q equals Lm. Alright, so this Q is going to be the heat lost or heat gained. M will be the mass. And we're going to use grams here. C is the specific heat. Think of the specific heat as the amount of heat needed to raise the temperature of a substance. Some substances heat up more quickly than others, and it has a different specific heat. And the change in temperature will be the change in temperature in degrees Kelvin. The second formula, this L represents latent heat. The latent heat is the amount of heat required to change phases for a substance. For example, if I were melting ice or freezing water, the temperature remains constant during a phase change. So the latent heat is the amount of heat required to change phases from one to another, and mass will be in grams. I like to use this staircase method to describe the energy transfer. As heat progresses to the right, and temperature will increase vertically. All right, so this portion will be in the solid phase. This portion is the liquid. And this portion will be the gas. Here along the first horizontal line, okay, since I'm dealing with water here, this will be 0 degrees on both sides. I can have ice at 0 degrees, or I can have water at 0 degrees. So If I'm going in this direction, I'm melting. In the opposite direction, I'm freezing. Same thing here. I'm vaporizing. In this direction, I'm condensing. And this will be 100 degrees Celsius. For ice, C is going to equal 2.01 joules per gram degree Celsius. The latent heat between freezing and melting, the latent heat for water is going to equal 334 joules per gram. The specific heat for water is going to be 4.184 joules per gram degrees Celsius. The latent heat of vaporization here is going to be 2,260 joules per gram. And the specific heat of steam is going to be 2.02 joules per gram degrees Celsius. So if I'm moving this direction, I know that it's going to be endothermic. That means it's absorbing heat. And if I'm going to the left, then we know that's exothermic. It's losing. When you're reading a problem, it's best to determine where you're at on the staircase. And then you can use the staircase to determine which formulas you have to use. Anytime you see a line like this, which have a change in temperature, I'm going to be using Q equals mc delta T. Anytime I have a line with zero slope, I know that Q is equal to latent heat times mass. So if you're working problems, it is best to memorize all these different parts of the little staircase. That'll help you a great deal when you start working problems. How many joules must be added to 10 grams of water to raise its temperature from 10 degrees Celsius to 45 degrees Celsius? So the first thing I'll do is I just sketch this out real quick. 0, 100. So we're operating in this area here. Okay. So I know that this area, I know that C is equal to 4.184. I know my formula, Q equals mc delta T. So we're going to say then that Q is equal to the mass, which is 10 grams, times the specific heat, which is 4.184 joules, times the change in temperature. The change in temperature will be 45 minus 10. So when I plug this in my calculator, I'll get 1464.4 joules. In our next problem, how many joules are needed to completely melt 25 grams of ice at negative 20 degrees Celsius? So the first thing to do, here's zeros, here's 100. We're starting at negative 20 here. And we're going to melt it. So it will be finished melting at this point here. So we have a step here, and we have a step here. So this is going to be a two-step problem because I had to go from negative 20 to 0, and then from 0 ice to 0 water. We're going to say then that Q is equal to mcΔT plus latent heat times mass. This will be from minus 20 ice to 0 degrees ice, and this is the melting of the ice. So the mass is 25 grams. The specific heat here is 2.01. The change in temperature is going to go from negative 20 to 0, so that's going to be 20 degrees, plus the latent heat for ice is 334 joules per gram times the mass of 25 grams. So plug this in my calculator, I'll get 9,355 joules. How many joules are released as 10 grams of steam at 110 degrees Celsius cools to produce water at 25 degrees Celsius? I'm starting at 110 degrees. I'm going to cool it down to 25 degrees. So I have one step, two steps, and three steps. Okay, so my first step, I had to go from 110 to 100. So that's going to be an mcΔT. I'm taking steam at 110. I'm going to 100. Now I have my latent heat times mass. I want to condense the steam. And then plus mcΔT to go from 100 degree water to 25 degrees water. Okay. So Q equals 10 times the specific heat of steam is 2.02. It's going to go from 110 to 100, so it's going to be a change of temperature of 10. The latent heat for steam is 2260 times the mass of 10 plus I have 10 grams of hot water, 100 degrees. Specific heat of hot water or water is 4.184. And the change in temperature, I'm going from 100 to 25, so that's a 75 degree change. Plug this in my calculator. I'll get 25,940 joules. This is the amount of heat energy that's released. So how much heat is needed to change 50 grams of ice at negative 15 degrees Celsius to steam at 140 degrees Celsius? So starting at negative 15, here's 0. And I want to end at 140 degrees up here. So I have one step to get from negative 15 to 0, a second step to change the phase, a third step to go from 0 to 100, a fourth step to convert hot water into steam, and then the fifth step to go from 100 degrees steam to 140 degrees. So Q equals mcΔT, this is for the ice, plus latent heat times mass, this is to melt, plus mcΔT, this is to go from 0 to 100 degrees water, plus latent heat times mass, this is to vaporize, and then mcΔT to go from 100 degrees to 140 degrees steam. So I have 50 grams. Specific heat is 2.01. The change in temperature is going to go 15 degrees plus 334, which is the latent heat of water, times 50 grams. Plus, now we want to mcΔT this, so this will be 50 grams times 4.184 times the change in temperature is going from 0 to 100, so that's 100 degrees. All right, let's vaporize that. So that's going to be 2260 times 50 grams. Now it's mcΔT, the steam. So the mass is 50. The specific heat is 2.02. And the change in temperature is going to be 40. Okay, so when I'm plugging this into my calculator, I get 156,167.5 joules. How much ice is needed to cool 300 grams of water at 25 degrees Celsius to 4 degrees Celsius? Assume the ice is at 0 degrees. All right, this is a different type problem. I have something hot mixed with something cold, so there's going to be a heat transfer. So our formula is going to be Q lost equals Q gained. Okay, so the water is going to lose heat. The ice and its melt water is going to be gaining heat. So for the left side, the water, since it's simply changing temperature, is going to be mcΔT. On the ice side, I'm going to have latent heat times mass plus mcΔT. This is the melt water here. Since we're going to end up at 4 degrees Celsius, once the ice melts, I have to heat the 0 degree water up to 4 degrees also. The mass is 300 for the water. The water is 4.184. The change in temperature is going to go from 25 to 4. So that's going to be 21 degrees change. That's going to equal its latent heat, 334, times some unknown amount, plus mcΔT for the melt water is the same amount as the melted ice, times 4.184 times the change of temperature. It's going to go from 0 to 4, so it's going to be 4. So if I multiply the left side, I get 26359.2. So 334 x plus 16.736x. If I add up my x's, I would get 350.736x equals, again, 26359.2. Dividing both sides by 350.736. I get my x is going to equal 75.15 grams. What would be the final temperature of a mixture of 100 grams of water at 90 degrees Celsius and 600 grams of water at 20 degrees Celsius? So I have a container here. This is at 90 degrees Celsius, and I have 100 grams. I have a larger container. This is at 20 degrees Celsius, and this is 600 grams. So when I pour these two together, what will be the final temperature? Again, we have a Q lost equals Q gained. So both of these are going to be an MC delta T equals MC delta T. So the mass lost will be the hot water, so it'll be 100 times 4.184 times the temperature. So the temperature is going to be 90 minus X. On the side, gaining heat. The mass is 600 times 4.184. And the final temperature is going to be X minus 20. You always subtract the smaller temperature from the larger one, since it's changed. So I know my hot water is going to be cooler. So I know my final temperature is going to be less than 90. And on my side that's gaining heat, I know that my final temperature is going to be greater than 20. Okay, the 4.184s cancel on both sides. So if I distribute here, I would have 9,000 minus 100x is equal to 600x minus 12,000. Combining like terms, so if I take this over, and if I bring this over to the other side, I would have 21,000 equals 700x. Dividing both sides by 700, I would have x is equal to 30 degrees Celsius. That would be my final temperature once both of these mix together. What is the mass of steam at 100 degrees Celsius needed to raise the temperature of 500 grams of ice at 0 degrees Celsius to 40 degrees Celsius? Again, Q lost equals Q gain. Okay, so the steam side is going to be losing. The ice side will be gaining. So the steam is to go into water, and then this hot water is going to go to a final temperature of 40 degrees. Okay, I have to melt the ice and then take the ice melt to 40 degrees. The latent heat is 2260 times some unknown amount of steam plus this unknown amount of steam times 4.184 times the change in temperature. Well, it's going to go from 100 to 40. So that would be a 60-degree change. The ice latent heat is 334 times the mass of the ice, which is 500 grams. It's going to change temperature. It's going to go from 0 to 40. So I have 2260 x plus 251.04 x is equal to 167,000 plus 83,680. Adding up all of our like terms, I have 2511.04x equals 250680. So x is equal to 99.83 grams of steam. Heat is simply energy in motion. By using Q equals mcΔT, we can calculate how temperature changes affect thermal energy, and with Q equals Lm, we can understand how energy is transferred during phase changes without changing temperature. When systems interact, the rule that heat loss equals heat gain allows us to track energy and solve real-world problems. Thank you for watching. Please like and subscribe, and I'll see you again soon with another video. Thank you very much. Goodbye.